do you do when you want to learn about somewhere? With a lot of places, you could just hop on a plane and go somewhere to investigate whatever it is you're interested in. But what if you can't actually go there? What if the place you're interested in is 140 million miles away and the material that you're interested in studying disappeared billions of years ago? That's the exact issue we run into when trying to discern the history of water on Mars. See, water, obviously, is pretty important. It's essential to life as we know it, and it's one of the things that differentiates Earth from almost anywhere else in the universe. A habitable planet, as they say, is a warm and wet one. Now we know that water exists on Mars in some form or fashion. Those aforementioned warm and wet conditions can lead to the formation of various minerals, such as clays like phyllosilicates, or hydrous minerals like serpentinite. We also know that water can form numerous geologic features, such as outflow channels or flood-like plains. Ice, wind, and volcanism have also played key roles in Martian history. For example, today we see ice present at the poles, though in the geologic past we think this ice could have been present at various latitudes, depending on factors like the overall climate or even the tilt. Today, water, ice, isn't really stable outside of the polar regions, and liquid water isn't really stable on the surface for long periods of time anywhere. But what were things like in the past? Let's find out. Our story begins roughly 4 billion years ago with the formation of the solar system. While the process of both planetary and stellar formation could be talked about at length, I won't go into too much detail here. Suffice it to say that planetary formation as a whole consists of 3 general processes: condensation, accretion, and differentiation. Even today, billions of years later, we can still find evidence on Mars that helps us uncover its formative history. Having begun to form roughly 10 to 15 million years after the initial formation of the solar system, the elements and matter that will become Mars slowly but surely coalesced, and over the next few million years, Mars as we know it today came into being. But what exactly went in to that hodgepodge of material that eventually became the 4th planet from the Sun? Today we can use geochemistry, isotopic analyses, and geophysics to help determine the overall composition of Mars and, by extension, what its formative history was. We can determine things like volatile abundances and lithophile, siderophile, or chalcophile elemental distribution. Authors like Taylor, Vanca, and Peslier have also looked at Martian meteorites to try and determine the overall chemistry of the planet. Other authors, like Elkins Tanton, have backed them up, saying that meteorites are, in fact, a good indicator of the overall composition of Mars. Still others have researched geologic processes in the planet and determined the rate at which things have happened. A good example of this is the quicker cooling and core solidification we know Mars went through, as evidenced by the hafnium-tungsten ratios present in the mantle. Back at the surface, while in the past there's been some debate over the overall crustal composition of Mars, today we know that the crust is largely basaltic, with some minor variabilities here and there. We find elements like calcium, sodium, magnesium, and iron on Mars' surface, while elements like the aforementioned hafnium and tungsten, among others, are found lower down in both the mantle and in the core. Once this formative process happened, Mars was what we would consider a fully fledged planet. And that's where our story really begins. See, Mars has a geologic history that in a lot of ways is similar to Earth. Both are rocky terrestrial planets that formed around the same time. Both have similar rotational speeds, and in the cosmic scheme of things, both are fairly similar distances from the Sun. But that's about where these similarities end. While Earth and Mars may have started out very similar, they evolved very, very differently. Martian geologic time is split up into 3 eras: the Noachian, the Hesperian, and the Amazonian. The Noachian lasted from 4.1 to 3.8 billion years ago and was dominated by superficial processes like erosion, as well as a number of impact events. Phyllosilicates and other clays were produced en masse during the Noachian, along with some sulfates toward the end of the era. Layered sedimentary rocks are also present, and oceans may even have existed. The Hesperian, which lasted from 3.8 to 3 billion years ago, was largely characterized by volcanism, reshaping and resurfacing much of Mars. Sulfates, that are still visible on the surface today, were produced for much of the era, which hint at a continued and sustained water activity, though less so, granted, than in the Noachian. The Amazonian, conversely, which lasted from 3 billion years ago to today, showcases many features that seemingly were formed by ice, with significantly less aqueous activity having taken place. Glaciation would have dominated, and possibly would have been influenced by factors like obliquity. Authors like Solomon in a 2005 paper note general trends, such as how the role that liquid water has played on Mars over time has gradually diminished from a fairly large role during the Noachian to much less of a role during the Hesperian and the Amazonian. Conversely, the role that ice has played has seemingly increased. Zhukovsky notes how the Martian climate has shifted over time, and how, even though, with the exception of polar ice, water doesn't exist extensively in a stable form at the surface today, it very well might have, and in fact probably did, in the past. Of course, each of these time periods I've just mentioned has specific characteristics about it, features associated with it, and certain geologic processes that likely would have happened during it. We'll look at a few of these processes in turn, and how each tie into the bigger picture of the history of water on the red planet.
One of the first things that strikes you about Mars is the seemingly huge basin in the northern part of the planet. This basin is referred to as the Borealis Basin, and through geochemical experiments, we know it's thought to have formed within about 50 million years of the solar system. Authors like Andrew Hanna in a 2008 paper note that the Borealis Basin was likely formed by an impact, and that it's effectively just like any regular impact basin that you might find. Now, I say regular there with quotes and inflection, as this impact would have been like any normal impact, just on a much, much larger scale, like a 2,000 kilometer or more wide crater type of scale. Of course, this then naturally begs the question, if there's a bunch of low-lying land over half the planet, is it ever possible that there was ever standing water there forming an ocean of some sort? Luckily, a lot of scientists have done work on this over the years, many going on to publish papers about it. Authors like Farron find landforms often associated with aqueous activity, and other features that can be interpreted as multiple seashore boundaries. Others, like Clifford et al. In 2001, point toward evidence such as outflow channels, and similar to Farron, what look like paleo shorelines. Authors like Diachilli back up Clifford's former point, while authors like Perrone agree with this latter. Clifford also postulates that these features hint at an ocean, and that this ocean was probably in the north, because, surprise, surprise, that's where the low-lying land from the dichotomy was. Clifford also briefly talks about the Martian cryosphere, and effectively helps once again tie together ice, oceans, and channels as part of one big interconnected hydrologic cycle.
On Mars, though, nothing is nearly as straightforward as it seems. If there was this ocean, or at the very least, large volumes of standing water present, what other evidence do we see? Surely Mars has more secrets than simply some ancient beaches or gullies for us to discover. Once again here, the answer is yes. As with many geologic processes, this purported presence of water has several other compelling lines of evidence that, while not necessarily indicative of the definitive presence of, say, life at any given location, nonetheless is likely indicative of water at certain localities.
A good example of this are the numerous clays, sulfates, and carbonates that have been found on present-day Mars. Authors like Millikan in 2009 and Ellman in 2013 point out that clays in particular would likely form in the presence of water, with Ellman noting that this could be done either hydrothermally, magmatically, or by some other mechanism entirely. This might have occurred at places like Jezero Crater, where clays like iron and magnesium smectites have been found. These clays and the structures they're found in are indicative of a delta that likely formed during the Hesperian. Aeolian features like dunes, transverse aeolian ridges, and ripples are also possible, possibly within these deltaic features. Others discuss the possibility of volatile-rich magmas, aqueous alteration, or even leaching. Millikan in particular goes on to discuss how smectites, again a type of clay mineral, would have mostly formed during the Noachian era from the aqueous alteration of basalt, further lending credence to water's role here. Still, other authors outline the transition from an early, warmer, wetter era with fairly moderate acidity characterized by polyosilicates to a later, drier, and more acidic era, this time characterized more so by the rise of sulfate deposits and sulfate minerals. This transition is thought to have occurred sometime around the beginning of the Hesperian era. As far as sulfates go, they're thought to have largely come from volcanic processes. It's thought that this transition might have been caused by the loss of the Martian atmosphere or from a change in the composition of what was being erupted. Any water at this time was likely relegated to groundwater-based interactions. Authors like Vanneman in a 2018 paper looked at sulfates like gypsum and anhydrite located in Gale Crater and determined that they would have formed over the course of about 1,000 years, but just under fairly dry conditions. Gale Crater itself has been pretty extensively studied. There's a noticeable gradation from clays to sulfates as one moves up the crater, denoting those changes in conditions we've talked about previously. As authors like Millikan note, this is indicative of the drying out of Mars as time progressed. Still, we see smectites and other clays scattered throughout Gale, leading us to the conclusion that aqueous processes did, at some point, play a role. We also find examples in Gale of the chemical alteration of some fine-grained sedimentary rocks, as well as outcrops of mudstones. These mudstones, located at Yellowknife Bay within Gale Crater, contain, in addition to sulfates, numerous clays, pyroxenes, and various mafic minerals. Authors like Ramp 2017, on the other hand, note the juxtaposition of jarosite and magnetite within Gale, surmising that to be a sign that water, while present for a time in order to form the jarosite, once again, slowly but surely disappeared, thereby not fully dissolving the magnetite we still see today. Jarosite has also been discovered at places like Meridiani Planum. It's, again, expected that jarosite formed under wet, oxidizing, and acidic conditions that would have gradually dried up over time, again, leading to sulfate formation. Hematite blueberries, or little spherules, basically, are also found at Meridiani. It's thought, given their locality within Meridiani Planum, that they're more a result of groundwater than surface water interactions, but nonetheless, the water still played a role in their formation. As far as the sulfate deposits I just mentioned, it's thought these came about due to a combination of sulfate and dust aerosols forming a sulfate-rich ice. Once this ice disappeared, the sulfate deposits were just left behind. Now, obviously, not all the ice on Mars sublimated away. Some was taken up into the poles, for example near the Planetarium region near the Martian North Pole, and into glaciers. In addition to giving us information about the current state of Mars's climate, we can also use these ice deposits to elucidate what the climate in the past was like. Authors like Head point out that if we can date when ice and sediment deposits occurred, we can tell from that what the obliquity might have been. Obliquity, as we've mentioned, has the potential to drastically impact climate and therefore the ice extent. As Joukowsky points out in a 1985 paper, higher obliquity would cause ice to sublimate from the poles and deposit closer to the equator. While this information can only help us discern the climate back to a point, it's nonetheless helpful in piecing together the aqueous history of Mars. Cold conditions, granted it should be noted, also lead to the formation of permafrost on Mars. Permafrost, effectively perpetually frozen soil, is common on Mars and has terrestrial analogs in places like the polar regions of the US and Canada. Similarly, groundwater, which is ubiquitous in many places on Earth, is thought to also exist in various places on Mars. Even though today this water is likely confined largely to the higher latitudes, in the past it's thought to have been much more prevalent. Some of this activity may have even helped to form some of the superficial features that we see on Mars today. Talk of all this feature formation, of course, naturally then begs the question, if both water and lava have the potential to carve out new land and form new features on the landscape, and if we know both of those processes were active on Mars in the geologic past, do we see any concrete evidence of channels or bases? Once again here, the answer is yes. Baker, in a 2006 paper, mentions the presence of what are believed to be fluvial networks, valleys, alluvial fans, deltas, and even, much like the aforementioned Clifford and Farron point out, paleo shorelines. While some of these channels and valleys likely formed almost 4 billion years ago, some, like Howard 2005 mentioned, are likely to be much more recent, having still formed, granted, when aqueous activity was fairly active, but much more recent nonetheless. These features include some eroded uplands and even some incision networks. Stack, in a 2013 paper, even goes so far as to use aerial imagery of numerous locations on Mars to explain bedding features, concluding that they're either airfall or lacustrine deposits. Other ideas to explain these channels, valleys, and networks include the since disproven CO2 turbidite hypothesis and the it still has some merit, so let's not discount it entirely, volcanic origin hypothesis. While this latter idea, proposed by the likes of Hamilton, Casanelli, and Leverington, still has some grounding in what we believe to be true, many scientists suspect that water played a much larger role than volcanism, due in part to the presence of the minerals and features already mentioned. It's also thought that hydrothermal activity could play a role in Mars' aqueous history. It's thought that a good amount of its activity might have resulted from large-scale impacts that would have imparted higher thermal energy into the impact site for a while post-impact. This is thought by some, such as Schwezner 2009, to have occurred especially during the late heavy bombardment. These impacts might have led to the formation of some of the amphiboles and serpentinites that we see on Mars today, and may well have also hydrothermally altered not only rocks that are on Mars currently, but also have altered rocks that would become meteorites and ultimately find their way to Earth. These meteorites have certain secondary minerals within olivine veins, as well as fluid inclusions and grains of augaite. These observations led authors like Bridges 2012 to contend that these meteorites' mineralogy was in fact the result of hydrothermal alteration in the geologic past. Some of the clays that we see on Mars can also be formed from hydrothermal alteration from CO2-rich solutions. This hydrothermal alteration is evidenced in places like Gusev crater. Several soil types are present in Gusev. Some, like the Pablo Robles soil, are suspected to have formed under aqueous conditions. Other locations within the crater, such as the Home Polite feature in the Columbia Hills region, are thought to have formed from a hydrothermally altered pyroclastic deposit. Hydrated sulfates are also expected around there. Authors like Ming also note that minerals like jarosite are present in the area, again, indicative of past aqueous activity. But what about present aqueous activity on the surface? Well, outside of any near-surface water or ice-related recently formed features, there isn't necessarily too much to speak of, with the exception, that is, of recurring slope linea. Recurring slope linea, or RSL, are just what they sound like. Flows of what are suspected to be either dust or water flowing down a hillside, disappearing and then reappearing again. It's thought that these features might be formed by processes as wildly different as deliquescence, ice melt, deep groundwater finding its way to the surface through fractures in a rock, or even just dry flows of silt-like material. What the actual answer is, though, is still largely up for debate. While many missions have detected RSL and the resultant change of their local landscape, none can quite agree on the exact nature of how they form or what exact mechanisms, be they freezing, granular avalanches, or something else entirely, are at play. So, we're back where we started. Now, where does that leave us regarding the history of water on Mars? Needless to say, things, of course, are complicated and intricately interconnected. While it's impossible to cover every last detail and every final determining factor that played a role in the aqueous history of our planetary neighbor, I nonetheless hope that in the last 20 minutes or so, things have become just a bit clearer. We've learned a lot so far, but there's still so much left to discover. Though that, I think, merits another whole video. I'm Dan, and thanks for watching.